The essential question for this video is, how does gravity affect objects? By the end of this lesson, you should be able to explain the law of universal gravitation and calculate the force of attraction caused by gravity between any two objects. Every object in the universe has a gravitational attraction to every other object in the universe. But because of the strength, we don't necessarily feel the gravitational attraction between us and the person sitting next to us. That's because the force of gravity depends not just on the distance between the objects, but also on their masses. The equation for universal gravitation is Fg, the force due to gravity, equals a capital G, which stands for the universal gravitational constant, which can be found on the front of your reference table. It is equal to 6.67 times 10 to the negative 11, and it has units of newtons times meters squared per kilogram squared. The unit for this is pretty much just to make everything work out right so that our force ends up being in newtons. This question says to calculate the gravitational force of attraction between a 60 kilogram student and the Earth. Assume that the student is on the surface of the Earth. When we're doing universal gravitation problems, it's important to realize that the r in this equation is the distance between the centers of the two objects. So in the case of a student sitting on the Earth, the center of the Earth to the center of the student is essentially going to be the radius of the Earth, which is why they call it r. When we're dealing with anything in circular orbits, the distance between the two objects will be the radius of that circle, which is why they use r instead of d. So if we plug into this equation, the universal gravitational constant, 6.67 times 10 to the negative 11th, times m1, the mass of the student, is 60. m2, the mass of the Earth, is again on the front of your reference table. It's 5.98 times 10 to the 24th kilograms. It doesn't matter which you call m1 or m2 because the force of attraction that the Earth exerts on the student will be the same as that which the student exerts on the Earth. And then divide that by the radius of the Earth, which on the front of your reference table, 6.37 times 10 to the 6th, and square that. Make sure you're squaring just the radius. And when you plug that into your calculator, you should end up with 590 newtons. This would have two significant figures. The 6.67 has three significant figures. The mass of the Earth and the radius of the Earth both have three significant figures on your reference table, but the 60 kilograms for the student only has two, so our final answer would have two significant figures. Using this information, we can actually calculate the acceleration of the Earth due to the student. Usually we think of the acceleration on the student caused by the Earth, but the Earth actually does have an acceleration caused by the student. It's just going to be a lot smaller because the mass of the student is so much smaller than the mass of the Earth. So we can use our equation from earlier in the year, F equals ma. We just found the force, and to two significant figures it was 590, but it was 589.79 something. You would keep that entire number in your calculator until the final step of the question. Equals, here we have the mass of the Earth, again received from the front of the reference table, times acceleration. And dividing both sides by the mass of the Earth, we get that the acceleration of the Earth caused by the student is actually 8.0 times 10 to the negative 21 meters per second squared. So the Earth actually does have an acceleration caused by the student. It's just very, very small, so small that we would not notice it. And I want to point out that this does have two significant figures as well, because the force that we're plugging in here, even though we left the whole number in there, it really only has two significant figures.